In the second part of this experiment, the circuit remains exactly the same. The only difference is that instead of a time waveform, we will be generating IV characteristics. So while the connections remain the same, you do need to change the channels in the sense that now this node is what you need to send to channel 1. That is, this signal will now become our signal X. That will be along the X axis in the XY plot. And know that we are trying to obtain IV characteristics, right? That means we need VD along the X axis and we need current in amperes along the Y axis. So what we will do here is that we will send this node voltage, which actually, accurately speaking, is VD plus 10 ID. But as we have discussed earlier, due to the very small value of ID, this can be ignored. Right? So this is what is going to serve as our VD. And to get the vertical axis, we are going to send voltage at this particular node to channel 2. Right? Why is that? Because DSO can measure only voltages. DSO is being connected across a particular element, right? Like this. As a result, you cannot really use it as a multimeter to measure current flowing through it. All it can measure is the voltage. Now, to get an indicator of current from this voltage is what we are trying to do. So, what we essentially say is that since whatever current was flowing through this diode is also flowing through this resistor, we connect a small value of resistor, say 1 ohm or 10 ohm, and we connect this to channel 2. Essentially, what we are saying is signal Y now becomes 10 times ID, right? But we need ID, and note that this is still in volts, but we need ID. So here what we do is for channel 2, we go to channel 2 settings and we select 0.1 as the probe factor. As a result, this now becomes ID instead of 10 ID, and we change the unit from volt to ampere. So what you are now showing on channel Y is ID in amperes. So this is how the circuit looks like. You can see we've connected a resistance, then a diode and a 10 ohm resistor. The voltage across the diode will go to channel 1 and that across the resistor will go to channel 2. If you look at the input, we are giving a 16 volt peak to peak triangular waveform. And this is how the waveforms look like. Know that now we need to change the property of channel 2. So we press the button of channel 2 and go to probe factor and make it 0.1x. We scroll down and then change the unit from voltage to ampere. Now this is showing I in the second channel, in channel 2. We will now press menu and go to XY plot. We adjust, we press both the buttons so that it comes in the center, in the origin of the screen. And we can adjust the scales to make sure that the waveform is spread out properly. Right? Of course, you can scale the values and obtain a proper characteristics like these. At this point, you should measure the cut-in voltage and the breakdown voltage, which are shown on the characteristics using the cursors, of course. And remember that these should match the values that you had noted from the time waveform in part 1. And whatever values you measure, please write them here. Know that in these characteristics, you also need to find forward resistance and breakdown resistance. So what you should do is select a point, any point on these forward characteristics, and then V upon I. That should give you RF, that is a forward resistance. Right? Know that this value, the point that you choose, should not be too much in the very high current region, because here it's almost a straight line, so resistance might come almost zero. And do not also take a point in this region, because here resistance will come out to be almost infinite. Take a point in this curved region, right? And of course, the higher you take the point, the lower will be the forward resistance that you calculate. Because current is going up, but voltage is not changing much. Similarly, for the reverse, for the breakdown, select a point in the curve region as much as possible. It is okay if this line is observed almost vertical and you cannot change it further, and the resistance is almost 0 ohm. That is also fine. But please make sure that you make that observation and save these waveforms, please. All these waveforms, the time waveforms as well as your IV characteristics. So those are the values that you will write here in this observation table. Moving to the third part, we've already discussed in class how a half wave rectifier works with or without filter. So as expected, theoretically in the first part, you are connecting the circuit like this, and you're going to give a function generator sinusoid input this time. It is not triangular anymore. Please remember, in the third part, you are giving a sinusoidal input. Okay, what is the value that is already mentioned in the description? And then you connect a 100 ohm resistance and you see the output in channel 2. So in the first case, what you can do is you can show the input on channel 1 and show the output on channel 2. Okay, I'm talking about the case where there is no filter connected. Okay, and you should observe as expected uh, this on channel 1, and on channel 2 you should expect a waveform like this. Also feel free to like roll up these waveforms and try to superimpose them on top of each other so that you actually observe a waveform that was discussed in the class, which looked something like this. Right. This is by rotating the knobs of the two channels, where you can move the waveform up and down and make them perfectly superimposed on top of each other, just so that we can observe this difference. Okay, this is from just from observational point of view. You're welcome to save the waveform in this form or showing them separately. This is again for the first part without filter. Okay. In this first case, please save the waveform and then know that you have to you have to fill in this observation table, right? Okay. So note that in the observation table, there is one section called theoretical and second is called measured. So theoretical is what, without actually doing this experiment on the DSO, just given the circuit, uh, what you could have theoretically calculated, right? And measured values are what you calculate based on your observations on the DSO. So while in the first case, when it says without filter, this gamma is Vrms upon Vdc the whole square minus 1. I'm sure you know the derivation of this expression and how it actually comes from this expression. If you don't know, please take it up as a homework. Please solve it. Right? But here essentially, since both RMS and VDC for a half wave rectified waveform can be written in terms of Vm, which is the peak value. So the RMS value is nothing but Vm by 2 and the DC value is nothing but Vm by pi for a waveform that looks like this, right? And goes up to Vm. You can calculate the theoretical value of what it is going to be. So it's going to be what, 1.21, I guess, right? For the measured portion, what you will do is on the DSO, try and display the value of VRMS. This is not something you are calculating, okay? So when you are displaying the values on channel, all values VPP, VRMS, V average, all this can be displayed. So display VRMS, note that value. Display VDC, note that value, and then calculate the theoretical value. This and this value should match each other. This is without filter. This is pretty obvious and direct. It is the second part where a little more calculation needs to be done. In the second part, because we are using a capacitive filter, R is already set as 100 ohms and the frequency is set as 1 kilo ohm. The theoretical value of ripple factor for such a case is given by this expression. Again, I leave the derivation of this expression as a homework to you. We've discussed it briefly in class, but you should know how this comes up. Okay. So given F, R, and C, you should be able to simply just directly calculate the theoretical values and write here. Okay. These are the different values of C which are given. Now comes the measured value, where the actual expression from a measurement point of view is given by this expression. VR peak to peak, meaning ripple voltage peak to peak, divided by 2 root 3 divided by Vp minus 0.5 VRPP. What does this mean? Think of your waveform. If this is your input waveform, which has a peak value of Vp, right? And once you have a ripple, your ripple looks something like this. The ripple voltage is this voltage. This is actually your VRPP, ripple voltage peak to peak. So to find the ripple factor of such a waveform, you know that ripple factor would be nothing but the RMS value of the AC component divided by the DC component, the average value. So in this case, the average value appears to be somewhere in the middle of this waveform. So that is the origin of this denominator. What would be this value? This height. This would be nothing but Vp minus half of VRPP. That is this whole thing. So this is approximated to be the average value, which is the denominator, average value of the ripple. So you get Vp minus half VRPP. And on the numerator, you've got VRPP divided by 2 root 3. Now we've discussed this in class as well. This term 2 root 3 is coming by the triangular approximation of this ripple waveform, because RC is much greater than time period. So what you need to measure in this third part is Vp, that is the peak voltage of the ripple. Okay, peak voltage, that means forget about this input waveform. You measure the peak voltage that you see for the ripple. Okay, then you also measure VRPP, that's this voltage. Put your cursors here and here, and then this value should give you VRPP. And put your cursor at the top of the waveform, and that should give you Vp. So you measure Vp and VRPP, write those values here, plug them in, and these expressions should match the expressions that you got theoretically by plugging in the values of R and C. Okay. In this experiment, please also note that it is asked what happens to the observed ripple as the capacitance of the filter is increased, right? So you need to explain your answer. So in the inference part, you should write the answer to this question. What happens to the observed ripple factor as the capacitance is increased? Okay, and why? Of course, the why part is also to be answered. Okay, so as you increase the capacitance, what happens to the ripple factor? Does it increase? That is, does it decrease? And why? Okay, please make sure to write that in the inference part of your report. I hope you enjoyed this experiment. Thank you and have a good day.